Welcome back, friends. Today we are going to deal with the issue of quantum tunneling. We are going to apply Schrodinger's equation to the issue of tunneling, and by virtue of that, what we are going to achieve that quantum mechanics, that classical mechanics could not. Now, friends, let us consider a finite potential barrier, and this finite potential barrier has three regions. Region 1 is the region before origin. I mean, it is x less than 0. Then region 2 is the width of the potential barrier. Let us consider this point as x equal to 0 and this point as x equal to L. So L will be the width of the barrier. And region 3 is the region in which again there is no potential. The particle is free. So here in region 1 V is 0, in this region 3 V is 0, and in region 2 the potential is V naught. Now if a particle is rolling down here in the region 1 towards this potential barrier, and that particle possesses energy less than the barrier potential, then classical mechanics suggests that the particle will not be able to overcome this, and there is no question that it will appear in the region 3. Now, here contradictory situations are observed in physics in the course of time, and they were, classical mechanics was not capable of explaining why things are happening like that. We are going to discuss in detail all the issues related to this. However, we shall go through the classical situation. Let us suppose that we have a roller coaster car. The car has no engine and has only wheels that can make it roll from point A, and it will travel towards point B. Now, the potential energy of the car at point A will be converted into kinetic energy and it will start rolling, and it will easily overcome this bump at point B and will go ahead. If the wheels are frictionless, then the maximum journey that it can make will be up to C. Now, if the car is found at point E, which is impossible because car on its own cannot overcome the barrier from C to D, and there is no question that car can appear at point E. But if it appears, what can be the solution? Classically, there is no solution to this situation. However, in quantum mechanics, yes, we can have solution, and the question is how. There can be a possible tunnel from C to E, and through that the car can emerge out, and yes, it is possible that it can appear at point E. Now let us come to a very basic issue that we have already considered, that in region 1 the potential is 0, in region 3 potential is 0, and here the barrier potential is of V naught, and incidentally we have a particle that is having energy less than the barrier potential. So in region 1 the Schrodinger's time independent equation takes up this form, where we can have K1 equal to under root of twice me upon h cross square. Similarly, in region 2, we have E minus V, and by that virtue we have different K2, and in region 3 we have again K1, same situation, no potential, free particle. Here x equal to 0 is that boundary region, and x equal to L is at the another interface, and width of the barrier is L. Now, the corresponding solutions to these three differential equations prevailing in three regions can be like psi1 expressed here, psi2 expressed as the last equation appearing on the screen, and psi3. So these three solutions are for three different regions. A, B, C, D and A dash, they are the constants to be evaluated from boundary condition. Now, every now and then we are going to encounter with these equations. So I have made a box on the right top corner. The equation, the wave packet, the wave function has to be continuous everywhere, and so at all boundaries, I mean both the boundaries. Let us consider the first boundary, that is encountering the particle interaction with the barrier at x equal to 0. So psi 1 and psi 2, it must be identical. Obviously, its first derivative also has to obey the continuity. Without that, the definition of wave function does not survive. Now, uh, for solving the differential equation and evaluating constants, we shall be requiring the first order space derivative of psi, and I am denoting psi 1 dash, and derivative of a into e to the power I k1x will be I k1 times a into e to the power I k1x. Similarly, you can figure out the derivative. I would advise the students to pick up a piece of paper and pencil and find out the derivative and match it here. Just pause the video and do that. It will help you. Now, the continuity condition offers that psi1 must be equal to psi2 at x equal to 0, that is the boundary point. And similarly, its spaced derivative, that is psi dash at region 1, is exactly equal to psi dash at region 2 at x equal to 0. So this is out of continuity. Now, the moment you substitute x equal to 0, it will be a into e to the power 0 plus b into e to the power 0. Here for psi2, again, it is c into e to the power 0 plus d into e to the power 0. So the first condition, that the wave function is continuous, offers you an equation a plus b equal to c plus d. For derivative to be equal, the condition that appears as x equal to 0 in this psi dash 1, you have to substitute x equal to 0 and e to the power 0 will be 1, I k1a into a minus b is equal to I k2 into c minus d. So this is how we have two equations. Now you can work out a minus b equal to k2 upon k1 c minus d. Now you have two equations and it can be solved for these two. So if you add these two equations, you can work out a, that is appearing in this highlighted bracket. Now the continuity condition at x equal to L. Here the continuity condition at x equal to L gives psi2 equal to psi3 and psi2 dash equal to psi3 dash at x equal to L. So here you can plug in x equal to L and using capital L, c into e to the power I k2 x is being replaced by L, then d into e to the power I k2 minus I k2L is equal to a dash e to the power I k1L. Now here, the in the third region we have taken only one part. The reverse part we have not taken because the penetrated particle is traveling in the forward direction. So that reverse condition we are getting rid of one constant immediately. Now we have this equation as derivative, and the this equation and the last equation can be solved for second constant, and C is equal to k1 plus k2 upon twice k2 a dash e to the power I k1 minus k2L. Thus we have evaluated two constants C and D from this condition. Now condition x equal to 0 offers you A, and the continuity condition at x equal to L offers you C and D. So you can make a complete representation of the constant A like this. Now A star and A dash star will offer us the transmission. The transmission T equal to A dash mod square upon A square. This will be the transmission coefficient, and a little substitution and paper and pencil work is advised for you to verify this equation. The transmission coefficient, in this transmission coefficient you can substitute K1 equal to under root of twice ME upon H cross square, and K2 equal to under root of twice ME E minus V upon H cross square. By substituting this, you approximately get T equal to e to the power minus 2L under root of twice ME V minus E H cross square. In a compact way, one can write that T transmission coefficient is equal to e to the power minus 2L gamma, where gamma is this under root. This represents a real quantity, that is definite probability of finding particle in region 3. The numerical calculation may suggest you smaller values, but yes, indeed, there is a possibility that the particle having smaller energy than the barrier can travel through the barrier. This is called tunneling. It depends upon mass of the particle, it depends upon the barrier thickness, and it depends upon the energy difference. Now here look at this equation, that the transmission is e to the power minus 2L gamma. So it depends exponentially on the barrier width, and then it depends upon gamma, wherein gamma is equal to under root of mass. So in fact, the transmission depends upon the mass of the particle. If the mass of the particle is growing up, it will be exponentially difficult for penetration. Again, it depends on the energy difference, how much difference is involved. So we are going to use this equation, which is approximated version, and T is approximately equal to e to the power minus 2L gamma. Now here you can see that a wave is hitting a boundary of barrier, and a feeble wave is entering into the region 2, and the portion is reflected back. This is happening in case of light. We have established examples, and like light wave, electromagnetic wave, we have de Broglie wave and wave packet. So matter wave also can penetrate. That is the concept here. So when the matter wave hits the barrier, the energy associated with the matter wave is much smaller than the barrier height. Then a portion is reflected back and a small part is traveling through the barrier. This is quantum tunneling. Now, something that we observe in case of electromagnetic wave similarly is happening in case of matter waves. Now here I have a paragraph from Ziox's book on quantum mechanics, and I would love to read that paragraph for you. When light is totally reflected at the boundary of glass and air, it actually penetrates into air. However, in this forbidden region, amplitude dies exponentially over a distance of the order of wavelength. No light escapes permanently, and we have total reflection. If we bring another piece of glass to within a wavelength of light of reflecting surface, light can escape into it even though two surfaces do not touch each other. So this is a schematic diagram that in the region 1 the matter wave is traveling and the energy of the matter wave is quite small as compared to the barrier height, and here in the region 2 the amplitude of the wave monotonically decreases and it emerges out. See, this wave is continuous. That continuity condition we have used while dealing with the differential equations. And in the region 3 you have a feeble wave whose amplitude has exponentially decreased in crossing the barrier. And with that decreased amplitude, it progresses further into region 3. Now here I would like to cite the example of radioactivity, and in radioactivity we observe that alpha, beta, gamma rays are emitted. Now alpha rays we are calling He24. So we have two protons and two neutrons, and they are emitted out of the unstable nucleus. Similarly, we have observed beta particle emission from the nucleus. So it was rather confusing at that time that how electron is emitted from the nucleus. So there was a question whether electron resides inside the nucleus because it is obvious like that. But later on it was clear that one neutron is converted into proton and electron. Proton is retained inside the nucleus and electron is emitted as a beta particle. Similarly, alpha particle is emitted, He24, two protons and two neutrons, that group is emitted out of the nucleus. Now, the energy of the alpha particle inside the nucleus is quite small, and it cannot leave the attractive clutches of the short-range nuclear force, and because of that it is anticipated that this bunch of nuclear particles cannot overcome the nuclear force. However, it was observed practically. Marie Curie has reported that observation that alpha particles are emitted. Classically, there was no explanation for alpha particle emission, and here quantum mechanics, after the Schrodinger's equation, it was established that yes, there is a theoretical explanation for emission of alpha particles. So here I have drawn a nice potential barrier, and it is on either side of the nucleus. We are having a sectional view, we are having one dimensional view of the nucleus. So nothing can escape that classically we feel, but alpha particle is escaped from this potential well. Now the practical situation is little different. The potential barrier has this kind of shape and not a square potential barrier. So this leads to some errors in the calculation that I shall cite as and when it appears. Now, from within the nucleus, the alpha particle is trying to hit the barrier, and the barrier width and the barrier shape, which is not a square potential barrier, it monotonically decreases the amplitude, and once it emerges out of the nucleus, the amplitude is retained. So here 241 nucleus is reaching to 237 and alpha particle is emitted. Now I shall consider V0 as the average potential barrier. So here the potential barrier is going this way. So we are considering the average potential barrier V0, and V0 cap is representing the average potential barrier, and the transmission coefficient is appearing like this. Here this quantity in the under root is gamma, and in this gamma, instead of V, we are using V0, and instead of the potential well size L, we are using R1 minus R2. So here one part corresponds to R1 and another part corresponds to R2. Now you can consider a simple square potential barrier, and the equation is like this for simple barrier. If you want to use V0, you have to use the earlier version. But both these equations are not giving very good result. So we need to correct the expression for potential, and here you can see twice Z E square upon R is the exact representation of potential, and that barrier potential has some nasty behavior which is not a square potential well. So here we have one integration which rolls from R1 to R2, and now the actual contour of the potential barrier is being considered, and this is a quite good equation. Now velocity of alpha particles within the nucleus is 10 power 7 meters per second. The radius of the nucleus is 10 to the power minus 14 meter. So the time t is distance upon velocity, and this is the striking rate. Here we have time t equal to 10 power minus 21. So the frequency is reciprocal of that time. So wall striking rate of alpha particle is 10 power 21 times per second, and the penetration probability is striking rate into transmission coefficient. So if you work out the probability, it will be 10 to the power 21 times the transmission coefficient. Now this is here tau is the disintegration time, and it is reciprocal of probability, and obviously probability is 10 power 21 times transmission coefficient. So the half-life lambda is reciprocal of tau, and it is approximately 10 power 21 times exponential of this quantity. Now this is very similar to log of lambda equal to a plus b into e. Now the penetration probability is uh, 10 power 21 into t, and the probability would be expressed like this. For alpha particle, mass can be replaced by 4 times mass of neutron. Energy E is equal to 4.2 mega electron volts. That is the energy of the alpha particle inside the nucleus. The potential barrier is 30 mega electron volts. Energy of the particle is 4.2 mega electron volts. And the width of the barrier is 2 into 10 power minus 12. By plugging in all these values, we obtain that P is equal to 10 to the power minus 18 per second, the probability. That is equal to 10 to the power minus 11 years. And tau is 10 to the power 11 years. So the disintegration time is 10 to the power 11 years. However, experimentally we find that this time is 10 to the power 19 years. This can be attributed to the unfair formula that we have used here, V naught, because the potential well is not square inside the nucleus. And if we replace T by this integration, exponential of this integration over R1 and R2, and here instead of the potential or average potential, we are actually using the potential of scalar electric potential of the He24, then here V naught is being replaced by this quantity. That leads to Ziegler-Nuttall law, which is log of lambda that is equal to A into Z upon under root E plus P. So inside the nucleus, we have nucleons present over here, and they have small energy, about 5 mega electron volts, and it has to overcome this barrier. So classically, there is no possibility of emission, but quantum mechanically, yes, the tunneling is possible. With 4.19 mega electron volt, there is a possibility that alpha particle is liberated from the barrier potential. Now here you can see that the alpha particle can be represented by a wave, and this wave amplitude monotonically decreases, exponentially decreases, and after it emerges out, the amplitude remains constant. Now we shall quickly go through an example. The example is now simple in the sense that we have a square potential barrier, and the energy of the particle which is hitting the barrier is 5.1 electron volts, and the barrier potential V naught is 6.8 electron volts. We shall consider the thickness of the potential barrier as 750 picometers. Now we are interested in finding the probability of electron being transmitted through the barrier. Obviously, being square wave potential, the problem is simple, and T is equal to transmission coefficient is approximately e to the power minus 2L gamma, where gamma is this one. And this is the situation which we have initially considered for discussion. And L can be substituted as 750 picometers. Gamma can be worked out for an electron. The mass of electron is 9.11 into 10 to the power minus 31. Here 6.8 electron volts and 5.1 electron volts difference is divided by charge of electron that makes it into joules, and h cross square is substituted in joule second. Now this calculation offers us T approximately e to the power minus 10, that is 45 into 10 power 6. I mean, that is the probability. So in every million electrons that strikes at the barrier, only 45 electrons can tunnel out. If you consider the same problem for proton, you have to only change the value of mass. So here 9.11 into 10 power minus 31 is replaced by 1.67 into 10 power minus 27, and by virtue of that you can calculate that the transmission coefficient is e to the power minus 186. But mind that this transmission coefficient, even though is very feeble, it is greater than 0. So yes, it offers a possibility that a proton will get transmitted through the barrier, and as the particle becomes massive, as the objects involved becomes massive, the possibility of penetration exponentially grows. Had this Planck's constant been a large value, the car could have penetrated in the drawing room. Thank you for your patient hearing. Thank you so much.